this is more an entertainment than anything else, but it does raise the question of whether this makes any sense. And don't take it too seriously. It's kind of a ramble, mostly a ramble through the history of analog computing. And I've only just learned about half the time I thought I had. So we're going to go a little bit faster perhaps than otherwise. This is my definition of an analog computer. You can read it, and of course you can later look at this thing if you want, because I guess it's being taped. But I think these are the essences or the ingredients of what we mean by analog computing. Continuous time, continuous amplitude, most importantly, concurrency, and that's very much like how we work in our head. Everything is happening at once. But of course, we recognize the limitations of analog computers, and no one today would want to put them up against a digital computer, particularly an exascale computer, which is just around the corner, I understand. But they're everywhere. And here's a question for you. What analog computer can you name that does this job and costs a penny? Well, maybe a bit more than a penny, but not much more. Well, I'll give you the answer right away. That's a 1 gram, 1 cell analog computer. It takes an input and generates an FFT of the input signal, and it does it immediately. So there's an example of how a device can do something quite powerful. And I make the note that analog computing, or rather I should say optical electronics, I meant to say that, is clearly around the corner in many different ways. So that's what it does. And there are many instruments that come to mind. And you know, behind these impressive front panels with their microprocessors and their clever digital displays, the key elements are often some very essential analog circuitry around about, if my mouse is working, around about here and around about here. What's behind the panel defines how capable that vector analyzer is. It's of course Agilent. Most of these examples are Agilent. Here we have scopes, which are a kind of programmable analog computer, if I can extend the definition. But they're getting more and more digital as time goes by. However, the interface between the signal we're trying to examine, which often, by the way, is a very fragile signal that we can't touch very hard, and the digital display, that's still all analog. It has to be. You cannot make an amplifier. Well, let me see if I can say this and keep my word. I don't think you can make an amplifier with digital components, except to say, well, an inverter is an amplifier. Yes, this is a special amplifier. Okay. Now, I have to add that nothing in that definition I showed said that it must be programmable. Most analog computers in the past have been, because they were doing jobs that at the time there were no digital computers to do. But nowadays, we're more interested in analog computing devices, which means linear integrated circuits, that do a very special job very inexpensively. And I'll later show you some examples of actual products that are in that category. So the question is, you know, can we do this? Would it be any use? Well, the answer to that last question is definitely. Already we're making revenues for the company out of computers that are of significant functional complexity for a few pennies, or actually selling them, I should say, for a few pennies. The so-called full factory cost has to be a lot less than that. There's this thing called gross margin, which means how much money can you make out of an IC, and it has to be way up there in the 80 to 90% region in order for the product to really gain traction in terms of the marketing folks' eyes. So here's another question. Is there perhaps some way we can get more out of an analog signal by keeping in the analog domain a bit longer than is customary? I mean, it's very customary today to get quickly into an AEC and do everything digitally, and that's understandable. There's all kinds of reasons why that makes good sense. But as an analog guy myself, I sometimes see things being done and I think, gosh, you know, I know how to do that with a handful of transistors. And I'll show you an example or two later on. Now, of course, analog computing goes back many years, and so I'm going to touch on a bit of the history. This is 100 BC, that's quite a few years back. And this really is a little analog computer. It's got gears. You can just about see them here. And it's apparently a mechanism for computing the position of planets or stars. We're not quite sure. It's been extensively studied, but it really is dated that far back. So we can say this is the beginning of analog computing. Oh, another gear there. And this fella, I don't know who he is, but he said he regards it as being more valuable than the Mona Lisa. Well, that's a matter of opinion, of course, but it certainly is a very, very interesting discovery, and it's been extensively studied and redesigned. So here's a replica of that mechanism, and I'll show you the person who designed it a little bit later. A very interesting character. This is an astrolabe. Again, this was to examine the motion of the planets and the moons. I don't really know exactly what, but it goes back to 1610 AD. Here's some Capetian scholars using an astrolabe around about 1200 AD. Heaven knows what they did with it. Only heaven knows what they did. This is a modern analog computer, and I say $1 by the dozen. That's about right. That gives you an idea of how cheaply now people expect ICs to be. It's very competitive. If you have a part that costs 9 cents rather than 10 cents, doesn't matter what the performance is, they'll go to the 9-cent part. That's a fact of life. So the performance still has to be good, even though it's very, very cheap. That's the challenge for the product designer. Here's a neurocomputer. It's yours, and for all of us, it's priceless. Neurocomputing clearly has a long way to go yet. It is the holy grail, if you like, of analog computing. But the limitation is the connection. How do you make zillions of connections between neural elements? That's long been a problem. The lateral geniculate nucleus, by the way, is a processing element that takes the output from the retina, which already is reduced by a factor of 10 in data rate by logic in the front of the retina. But that signal goes to this thing, which then expands it into billions of channels and does some computing before it finally goes to a later part of the brain to tell you what you're seeing. I don't understand how it works. I just know it's a big analog computer that we have. This guy, who's wearing a watermelon, half a watermelon, but he is William of Oughtred. And in this era, he invented the slide rule. And this is a picture I took in the Science Museum in London of a slide rule of that type. It's not his, but it's of that era. And it's really remarkable to think that such things were being developed at that time when mathematics was still had a long way to go. Oh, I don't know why that's in there. That's my home lab. That's not supposed to be in here. Sorry. Here's how a slide rule works, in case you don't remember. You do remember what a slide rule is, don't you? I hope. Do you? Anyway, a slide rule is a little computing device, and you can multiply numbers. Basically, the idea is you divide up the scale into 2 logarithmic scales, you slide one against the other, and the sum of 2 logs can be read back, and instead of having to mess around with some kind of funny product, it's just a summation. Now, that idea is the principle behind a lot of modern analog circuits, this idea of using logs to do interesting things. Here, multiplication, but they can do many other things as well. By the way, it's interesting, there is this website where you can play with this slide rule. You can actually move it up and down and do things with it. Now, you can do the same thing with transistors. For a reason which we'll get to in a second or two, if we apply a current to the collector, or it could be a device, MOS device in subthreshold, we'll find that the base to emitter voltage, or the gate to source voltage, follows a logarithmic relationship. In a bipolar device, it's so accurate that, for example, we can sell a product. I can give you the part number, ADL5304, which claims a 200 decibel range of current measurement from 1 picoamp to 10 milliamps using such a device, or devices. So this really works. This is not a joke. I'll tell you when it's a joke. Now, if we take another of these devices and do the same kind of thing by somehow forcing its collector current, we have the sum of 2 logs, which of course is a product. So that's the basis of multiplication, but we're jumping ahead a bit because we've got to do the history bit first. In 1904, Edison discovered an effect which he didn't make any use of, and he kind of discarded it. But a guy by the name of Fleming decided that there was something to be sort of examined here, something useful. This, remember, was a time when radio was just beginning to take off. The detectors were crystal detectors. They really were semiconductor detectors. And as a matter of fact, the whole history of the semiconductor industry started with galena crystals, which is, what is it, copper, galena, oh, never mind. It's a detector, it's a semiconductor. Anyway, this is a real tube from the Fleming era. I wish I had it in my museum. It looked like an interesting device because it was a rectifier. Well, along came this fellow called Lee DeForest, who put a grid between the anode and the cathode. I didn't name them before, but I think you can see what they are. Cathode is the little red gizmo, which is hot, emitting electrons, which are attracted to the plate by an E field. And he put a grid in between here, which you can actually see looks very much like the squiggle in this little diagram. It's just a bent piece of wire, and that really is one of the earliest triode tubes. Triode tubes became very important. Here's some devices called audions, which are triodes, believe it or not. But what I found interesting about this was the annotation at the top on the patent for space telegraphy. Now, here I think by space it just means distance, but it was kind of a strange prophecy, wasn't it? This is from my own collection. I love tubes. I've got zillions of them. Some of these are old and some of these are new, but this is the kind of thing that I have in my home lab. And I could tell you more about them, but we don't have time. Except I'll mention this is a magnetron, which is a very, very important tube concept. But that's time for another lecture. Some of these things bear all these cautions about, you know, don't get too close to the waveguide, it'll blow your brains out. Which so we don't do. Anyway, World War II was very important for me because after the war, there was this huge glut of surplus equipment for pennies. Talk about penny computers. I mean, they weren't quite pennies, but they were very, very cheap. And people like myself, and I found out by his bio from Carver Mead, he had the same experience. We bought this stuff and we took it apart and we did stuff with it. And it was a great time for a learning youngster to get his hands on real electronic equipment. I built my first TV with some of this X-radar stuff when I was 11. So that gives an idea of the potency of the stuff. So, what was important about analog computers? I'm going fast because of the clock, excuse me. But these are some of the applications that were important during the World War II years, and you can read for yourself what they are. But two at the bottom are probably rather important. Missile developments, which is something that unfortunately is rather distressful to me. But anyway, missile guidance was a driver of miniaturization of electronic components. And the bomb, of course, was a driver of simulation. Nowadays, we use those same computers or bigger ones for weather prediction, which seems to me to be a more sanitary thing to do. Now, this is rather interesting. You might look at this and think it's an analog computer. Well, I make the point it isn't. But what it is a power supply for an analog computer. And this is some of, oh, there's a little Dumont scope up there. But anyway, this is some of the text, which I find interesting. It's a 4,000 tube computer, but notice it says, this is a research engineer's dream. Well, it's a nightmare as far as I can see. Anyway, and they could control their voltages to within 0.001%, that's a bit surprising. And they used a three-phase power supply. So I think that is not exactly what we're talking about today. We're trying to get down to the penny level, so let's discard that. This I'm going to go over, it's an analog mechanical computer, it's a bomb sighter, but I won't tell you more about that. But this one is interesting. This is a replication from the real equipment from a Vulcan bomber, which was a British bomber. And it is, again, it's a bombing computer. It's too bad these things have to be used that way, but that's what it did. But what's fascinating about this isn't the display of this device, but the gal, a lady, who put it all together and remade all these cables. I mean, you can see there's a lot of cabling here, you know, with special connectors. She reconstructed all this to get this thing to work. That's what's amazing. Now, of course, she wasn't dropping bombs, but, you know, everything worked. And this is the lady, back view. And her name is Tatiana. And this is front view. She's an odd gal. Tatiana Van Vaak. And on her equipment, she always puts TDT Fesset. TDT made it. And this is one of the things she made. This is called a harmonium. It's mostly mechanical analog computer for the analysis of spectra, basically. But it's mechanical, and if you look inside, it is beautiful. Now, she makes all those things in her home workshop. I mean, it's a big workshop, but she makes the gears. This is not something you buy on eBay. And I think she's an amazing character. I would love to meet her. Anyway, a little bit about op-amps. The symbol that the company uses, Analog Devices, is a figurative op-amp because op-amps are important today. I understand we've got about 1,000 different op-amps in the catalog. Goodness knows why you need that many op-amps, but somehow they came into being. I think some actually are differential amplifiers, but basically about 1,000 different amplifiers in the catalog. Now, the idea behind the operational amplifier, I hope, is well known to you. The idea is that something pretty tiny at the input makes something pretty big on the output. So the tininess is allowed to vanish in our calculations. And then the actual operation is in the feedback path. And it can be a lot of things. It can be passive elements, passive nonlinear elements. It can also be passive and active nonlinear elements. You can do a lot of things, but the basic idea is that the function is defined entirely by that thing underneath and not by the amplifier on top. Not true, but it's a good idea. Well, you know, I mean, it's sort of basically true. And also we can put in time-dependent elements, of course. Okay, now, I want to make a point. Well, first of all, op-amps are passé. There's too many op-amps in the world. They're too easy to design. We don't need to write anything more about op-amps, do we? Well, maybe we do. Anyway, this is the idea that I carry in my head as to what an op-amp is. It's just an integrator. It's not an amplifier that fails to respond well at high frequencies and has some pole of about 1 hertz or so. It's an integrator. And the fact that it doesn't have infinite gain at low frequencies doesn't matter. There are very few applications that require a DC gain of 100,000 or more. Just think about it a bit, and you'll realize that the external components determine the accuracy, not the op-amp gain eventually. There may be a few applications where the gain needs to be high, but basically that's it. So now being an integrator, there has to be associated with it a time constant. Otherwise, you know, the integral doesn't work out right. And that is, of course, the integrator's time constant. It's a C and an R, or GM upon C, but it defines the frequency of this ideal device called an op-amp. And that is the response that we should expect from an ideal op-amp. The gain should go to infinity. That takes care of the zero input voltage at DC. But it does have a frequency at which the gain drops to ×1, or 0 dB. And at some low frequency, it limits out at about 100 dB. We know that, that's common practice. But think of the op-amp as an integrator with this as the fault, not the other way around. In other words, it's not the fault that the high frequency response gets bad, you know, that the response gets bad at high frequencies. The problem with an op-amp is that the DC gain is finite, but that doesn't matter generally. Op-amps have that nice aspect to them. And of course, at that point, because this is a simple single pole response in a dominant pole, we don't always use dominant pole compensation nowadays, that's true, but in a classic op-amp of the type I've shown a second or two, if the DC gain bottoms out at 100 dB, that's a corner, but the corner occurs at the unity gain frequency divided by, in this case, 100,000, which is 100 dB. So if this is, say, I don't know, a megahertz, that's only 10 hertz. But that corner is not really a characteristic that matters. What really matters is this F1. That's the important point. And this region I've shown is the redder the region, the more useful the part is, until eventually, well, it really should have just a region in the middle, I suppose. It's not going to be much use down here, it's too slow, and eventually it's going to cop out with finite gain up here. So really I should have shaded the middle area. But this is the place where we're using op-amps most usually. We're not bothered about the gain of DC, we're not bothered too much about what funny things happen at high frequencies. I shouldn't say that, I know it's a generalization, but from an operational amplifier perspective, as an analog computing element, this is the sort of basic idea. Here's a very early Philbrick amplifier, I've got quite a lot of these at home. One of the guys came to Analog Devices from Philbrick, he's just retired at 86, Dan Scheingold. And he loves these things, and I love these things too, but we have to move on. But I just want to show you something about that amplifier, which is kind of interesting. It runs from a minus 300 volt supply and a plus 300 volt supply to start with. It consumes a lot of current, and the bottom line here, somewhere, it uses some neon tubes up here as stabilizers. It has a tricky little feedback thing here, which is meant to make the gain infinite at DC, or the other way around. It'll flop over and come back again. Anyway. But look at the power. Here it is, 1.7 watts for one operational amplifier. Okay, not quite in the league we're in today, but it started things. So here's a computer you could buy for about $1,000, Heathkit, and it had about 15 of these kind of op-amps. not Gilbert, but something like them. So we can say, okay, then that's a benchmark. A penny analog computer should have at least 15 op-amps, let's say. Now, if we consider the price of 65 nanometer stuff, you can get about 1,000 transistors for a penny. So we're in budget as far as the op-amps go. But we still need to do some nonlinear stuff, and that's where I get interested. Here again is an actual example. I put this a little bit differently, but 10 cents by the million is what that's supposed to say. That's the sort of quantity these parts are used in. And it's very gratifying to see circuits that one has designed that sell by the tens of millions. And they all work. And that's really exciting. Battery isn't included, of course. So I want to talk about multiplication because it's one of my interests, special interests, I suppose. These are some of the early methods. They were mechanical, using servo motors and potentiometers. There were ideas using modulation of pulse width and pulse height and pulse width, and then averaging. Something called the quarter square approach, and then even some special CRTs with specially shaped masks that were supposed to make it look like actually a parabolic function for some reasons. But I mean, I know the reasons, but I don't want to go into them. And then some curious tubes, which I'll show you in just a moment. But anyway, here's a servo multiplier. This is one of Tatiana's pieces again. That one was something else. This is one of hers. Look how beautifully made that is. I mean, I get pleasure just looking at this stuff. I don't know about you. No, really. I mean, whether it does something or not, it's just lovely to look at. And you notice here, this is interesting. This is a Tektronix style of little strip. They had ceramic insulators and little. Anyway, that's from Tektronix. Somehow she got some. Okay, now some of the problems with any mechanical system, of course, are all these. And these are problems shared by some circuits as well, apart from mechanical stuff. So they have to be dealt with, and nowadays we resort to laser trimming. I'm not ashamed to say it. It doesn't cost all that much. Someone was asking today, how much does it cost? Anything from 1/10 of a penny to about 2 cents to do a complicated laser trim. And it's really a very powerful means of improving the performance of a circuit without having to deal with some complicated digital engine that does it all for you, which I know is of interest to you guys, but we're lucky to have laser trimming, and we're going to stay with it. Anyway, going back many years, this is what's called a parabolic multiplier. It used a bunch of diodes making and a resistor string that made a nonlinear parabolic function. Very, very crude. But the idea was that if you take x plus y squared and x minus y and square it, then you end up with 4xy. That's the basis of a parabolic multiplier, sometimes called a quarter square multiplier. And in this example, this is a Telefunken analog computer, it goes back many, many years. There are 8 of these analog multipliers in this device. So this huge machine with all of this wondrous helipots and things, it only had 8 multipliers to do the job. Well, okay, maybe that's all they need. Here is a curious, this is the CRT I was telling you about. So here we have an electron gun. It doesn't look like much in this drawing, it's a square block. But anyway, that's a triode electron gun. Then we enter a pair of deflection plates, and as you move the beam left and right, as you can see it would be, with this particular orientation, you move across this shadow mask, and what comes out is the square, where's my pointer gun? Is the square of the signal. Very, very crude, and yet in 1950 this was a record to be something of an advance. Here's another strange thing. I don't remember exactly how this works, but it's basically a pentode that's used in a multiplicative mode. And people went to all kinds of lengths to make squaring cells just to implement the quarter square principle in multipliers. Here's a time to height multiplier. So we have an input Y and an input Z, I think here. And we're doing switching here. These switches are concurrent, so they're looking at Y and Z. VZ, by the way, is a reference. I'm trying to find, here's X, excuse me, yeah. So we're integrating X and comparing it with 2 references here. And then we're integrating Y. And the long and the short of it is that when this thing runs, as it will because of the reset flip-flop here, the output is the average of the output is a product divided by VZ. There's always, of course, got to be a denominator. If you multiply two voltages together, you have to worry about where that denominator comes from, because it sets the scaling of this thing. Anyway, I made a circuit just to sort of try it out myself. And here are the switches. By the way, this is interesting because this is SOI, and in a silicon non-insulator process, you can use bipolar transistors as switches, provided there's somewhere for the base current which turns them on to go. And in this case, the base current can go into these voltage sources here and here, and we can commutate from the positive or the negative reference to the positive reference using bipolar. And this really works. And it's interesting because the offset of these devices can be very small, just millivolts, which is not what you'd expect from the structure of the device. Anyway, so I made this thing and tried it out, and here are some results, simulation of course, just to prove the point. And here is this is the kind of the raw output. Here it is filtered a little bit, and sure enough, if you try it out, it does indeed provide the product of two inputs. But you can see it takes about 10 milliseconds to settle. So that's not what we're after right now. I think the discovery of the translinear principle was kind of a breakthrough, because suddenly we could make these multipliers in monolithic technology with just a handful of transistors, and it really made a big, big difference. So here's our two multipliers, two transistors we had before, but it's really only half the story, because so far all we've got is the logarithm of the product, which really isn't what we want. We want the product itself. So let's take another little fundamental cell, which we're very accustomed with, and we discover that this isn't showing it very well, but this is a complementary pair of currents, and in order for that, and of course the tail current here would have to be I in this case, and the voltage that has to appear across the bases to do that is the difference of these two. So it's log x over 1 minus x, and that voltage is very precise, and that's the thing that is so endearing about the bipolar transistor. I know that we can run CMOS in subthreshold or near subthreshold and get similar kind of performance, but these devices really meet the challenge. They do wondrous things, and I'm sort of hooked on them, even though I do CMOS with a bit of regret. Well, you've got to do it. So this is the heart and soul of the BJT. The fact is, there's only one equation that matters, and where I sub S comes from, we don't have to worry about today. VT is the thermal voltage, KT upon Q. I sub S, though, is a very interesting thing. This is not I sub S, this is the density of states, I guess it's called, the square of density of states, just due to thermal behavior in the material. But it has these wonderful numbers in it: 32, pi, Planck's constant, the mass of the electron hole, temperature, Kelvin, raised to power 3. It's very, very fundamental. And that's why bipolar is so different to CMOS even in subthreshold. Because CMOS in subthreshold is still empirical. The bipolar transistor is rooted in some very, very deep physics that always works. So let's make that multiplier. We'll take the input stage, we'll stick another pair on it, and we'll make a few connections here and there, like the bases have to be connected, and we've got to supply some currents. But what we end up finding is if we can force 3 of these currents, then the third current is the product of 2 of them divided by the third. And that really, really works. That's just a practical realization using the 4 transistors and 4 op amps. These I'm going to jump over. This is a product that's very accurate. I think it's the most accurate multiplier available, although I'm not absolutely sure of that. That was designed many years ago. And this is what's inside. I'm jumping over these because I see the clock. Well, this is how it started. People have made reproductions of this, and I almost bought one on eBay, but I was outbid a while ago. I'd like to have one of those around the place. But anyway, 50 years ago, this is how the bipolar transistor was viewed. I call it the beta view. Oh, you're running yourself now, is that it? Well, okay, I'll just watch. You better stop, otherwise I'm gonna, okay. So, all I want to say here is if you look at the transistor a little bit more carefully, you'll find it has structure, and that structure is like a slide rule in the emitter. That is to say, oh, come on, give me a break. that the voltage developed across the base emitter junction is reliably like a slide rule in as much as it's a logarithmic function of the collector current. Here's a translinear loop. Here we assume all of these devices are perfectly logarithmic junctions, just for the sake of this discussion, and then we'll do some calculations based on that. And you find out, of course, that the forward voltage of each of these devices is proportional to the log of the current density, that much we've established, although quickly, and that the sum of the voltages must be zero around the loop. Well, if that's the case, you can equate things and find out that the product of the clockwise current densities must be identical to the product of the counterclockwise current directories, counterclockwise currents. And that's the basics of the Translinear Principle. And I have to say here, as I've said already, the bipolar transistor retains unique properties which I don't think are matched by any CMOS technology. And that, of course, is why we're so excited these days about BiCMOS. We have a great what should we say, access to BiCMOS processes. In particular, one that I like to use is a heterojunction complementary bipolar combined with TSMC 0.18, which is really a lovely combination. 0.18 may not be the end of the road as far as CMOS goes, but it's enough for a lot of purposes that we would use it for. And of course, this idea of the translinear principle applies to each to heterojunction bipolars, which are just bipolar transistors anyway. So I believe in the bipolar, and I say that only because I know it's sort of going out of fashion. Here's a little teaser. Given the translinear principle is true, that is to say that each of these VBEs is proportional to the log of the current, how would you calculate what that center current is, given the two outer currents? It looks like two current mirrors working together somehow. What does it do? Well, a back of the envelope calculation will show you that IZ is the vector sum of X and Y. And that's all done in the space of, what, 7 transistors. Here's another teaser. I won't dwell on it except to give you the solution. It's the vector difference. So that gives you an idea of how much power you can get out of just, in this case, 4 transistors. And it would take a fair amount of processing to do a vector sum of 2 quantities. This is another example of how useful this idea is. It's an analog array normalizer. I made this as an IC, but it never went into production. But it had 16 input channels, each of which could handle a 60 dB range of input current. Actually, it was input voltage by the time it was finished, but a 60 dB of input. And the idea is if you have an array of inputs, like from sensors, sonar sensors, or seismic sensors, the information of interest is in the ratios of the signals, not the absolute value. The same is true in speech recognition. If you divide up speech into, say, 16 channels, by resonant filters, the information is in the relative magnitude of those outputs, not in the how loud you speak. So I thought this was a neat idea because it does the job of normalization in one go. The output of any of the inputs is equal to the the output of any of these transistors is equal to the input applied to the associated diode divided by the sum of all the inputs times the tail current. And in fact, the actual circuit had a feedback path so that it could make one of the outputs at a standardized amplitude to drive an ADC, and then all the rest fell into place in the right ratios. Log amps we've made a lot of. I think I'm going to jump over them quickly, but we've done a lot of log amps at the Northwest Labs. We're now up to about 28 gigahertz or thereabouts, and they're very easy to use, and they're very, very powerful in having very high dynamic range. These are just a few of the parts. This was made years ago, and I think it's about twice as long now. The idea is, oh, please don't do that to me. The idea is you have a series of gain stages of moderate gain, so therefore considerable bandwidth. And each node, it's really differential, but each node has an associated detector, which might be a little square little detector, 3 transistors worth. And what comes out is a current mode signal, which when added all up together, when all the sums are done right, it turns out being a good approximation, a very accurate approximation to a log function by the maths, which I show in a paper somewhere or another. I wanted to make log amps just as easy to use as op amps. So, putting it into an 8-pin package was part of the story. But this is a real part, and it's very easy to use. A more recent part called the 8310 comes out scaled a bit more nicely and a little bit of an advance. But it's very easy to use these things. And log amps never used to be that way. They were big, hunking, gold-plated boxes with SMA connectors and lots of power and so on and so on. So that's been achieved. And here's an example of how one of these log amps, in association with a VGA, this is called an X amp, together can cover 120 dBs of measurement range by putting a bandpass filter to cut down the noise of this first VGA. And it's matched at the input to 50 ohms. And it has this very, very big dynamic range as a measurement system. The log output is here, 10 millivolts per dB. These are not exactly analog computers, but the function is a computing function of a kind. And then we're doing microwave power detectors. I talk here about true mean square. And many signals today don't look quite this deep modulation, but they have a lot of complex modulation, and people want to measure the true power. And so we've developed a whole bunch of parts that do that, and I'm jumping around, as you can see. Basically, a simple method is just to square the signal and then deliver that, but that's not very satisfactory. The next step is to put another squaring cell in a feedback path and make this voltage equal the RMS value of that voltage, and now you have a true root mean square at the output. Here's another one of these RMS converters, another little 8-pinner, and I show here with use of 2 variable gain amplifiers and a bit of external componentry, again you can cover 80 dBs of log RMS. And you can argue about whether that's computation or not. It's low-level computation, certainly nothing to write home about. Then John and I, where is John? Is he here? Oh yeah, John and I developed, I wish I wouldn't do this, don't know why. We developed this almost a network analyzer chip. It's called the 8302, and it's really 2 log amps and then some differencing circuits at the output. And you can use it in a lot of interesting ways. The interesting thing about taking the log of a quantity is that if you measure 2 voltages A and B, you get the ratio of these 2 voltages at the output independent of their actual magnitude. And that's often more important because, for example, you want to measure, well, I think I've got a picture here. Oh yeah, that just shows that the bond wires don't get in the way too much because they're equal in both paths, and so any peculiarities about the RF response due to bonding is equal to both log amps. It's a nice little part. We keep saying we should make another one that's faster. But it's got a phase detector on the output as well, and it's got a lot of applications. I'm going to jump through this because I'm supposed to stop very soon. But here's an example where you have a coupler. There's a power amplifier here that's delivering power to, say, an antenna, and by coupling the signal in the 2 directions, you can measure the gain, or rather loss in this case. Well, you can measure a couple of things, but you can measure basically the ratio of the load voltage to the source voltage, and sometimes you can use that for antenna tuning and other things. But it's a little network analyzer. It's not quite Agilent yet, but it's almost the front end of an Agilent machine with all that wondrous digital stuff behind the works. This is another way of doing true RMS. We have a VGA here, which is, I call it X amp, that means exponential amplifier, exponential gain in relationship to this voltage. And this serves to take an input signal and change the amplitude down to the point where the input to this squaring cell is identical to the DC reference applied to another squaring cell. And we integrate the error between the 2 and feed that back to set the gain. And really, it's kind of like AGC in a radio receiver, except it's a bit more sophisticated. And it does true RMS computation of signals up to microwave frequencies. These are real products, not just suggestions. And then I also want to mention that in making a sine-cosine quadrature of this kind, 2 GM upon C's chasing each other, if you do it differentially, you don't have to worry about the inversion. So 2 identical GMs, and it's a nice idea, but the question is, how large is the amplitude? If you let it run itself, it'll become a relaxation oscillator. It won't any longer generate sine and cosine, it'll generate 2 tri-waves. So you've got to do something to set the amplitude. We've got a frequency control, which is the GM control here, which sets the frequency. That's fine, but we haven't got anything yet to control the amplitude. So what I've done is I've taken 2 squaring cells, and if you take the square of this and the square of that, you end up with unity. So it's cos squared plus sine squared is unity. and you compare that to a desired amplitude and feed that back into some damping diodes that tell this thing to stop getting any bigger. So you can end up with a very low distortion sinusoid, sine and cosinusoid, and if you want to use it in, say, I and Q applications, you have to buffer it and turn it into square waves for the mixers and so on and so on. But the basic idea is you've controlled the amplitude by design. I like to say what we're doing is achieving performance by design, not by luck or by using what someone else did, but always designing into the part performance that we desire it to achieve. In other words, you must feel, if you get into an industrial career, that you are the masters of these devices called transistors. You tell them what to do. You don't let them tell you. No, I'm serious. I mean, they are your characters, your actors on the stage. You choreograph what they do. You don't let them get away with murder, because they will. This is not too interesting, but I did a universal trig function generator years ago. It was quite a tour de force in terms of nonlinear function generation. It generated all these functions: sine, cosine, tan, cosec, secant, cotan, and inversion functions as well. And it was obsoleted because it was too late. Microprocessors came along, and that goes into that. But look at how simple the core is. It's just this thing, which I call a Kermit, which stands for common emitter. There's the common emitter. Hello, there. Common emitter multitangent. Multitangent is something we'll have to talk about another day. But this ends up generating this function. It wiggles. In this case, it wiggles a few times. But in the central portion, it is very accurate. In fact, the accuracy of the part in the specs page for the 639, I think it is like, I think it's 0.02 of a degree. Scaling, I forget exactly, but it's very precise. And of course, everything is temperature control because you do all the right biasing stuff. Biasing technique is 70% of the challenge, and 30% is the signal path. You must get your biasing right. It's very, very important. And this shows, here is the actual function, and I've overlaid a pure sinusoid on top of it, and this is the error. And in this case, this was just a quick simulation. The error was plus minus 0.5%, but the actual part is better than that, partly because it's laser trimmed. So here were just some pictures taken for the data sheet showing various things it does. Here's the spectrum of the sine wave. This is the tangent function, the arctangent, arcsine, and so on. So it really does all these things. Then another part was called the real-time computational unit, so we're getting a bit closer to analog computers, and I'm getting a bit closer to my time limit. So I'm going to jump over that. Here's an idea. Can we make an analog computing element which is sequential? Now that takes away some of the appeal of analog computing, which is concurrency. But maybe we could do something with this. So here's what I have in mind. Okay, I'll leave that on long enough for you to quickly see what I'm limiting the performance to. We've only got a penny to spend on this thing. So here are a number of analog computational units which can be sequentially selected. So here's an input. We'll select this unit first, and we'll close that switch and put it back to this node. So that switch remains closed for a while the interim result is sent to the next computational unit. So it's a series of computational units which only act in series. And of course, being sequential, a lot of the power of analog computing is taken away from it. But it's just something I'd like to make one day. It goes into an 8-pin package. It's got a 1.5 volt supply, a serial data interface to control it, and in and out. It's kind of it's not a pipe dream. It's not a pipe dream. I think it's possible. But whether it really qualifies as a true analog computer, I leave you to imagine. Really, neural computers are as I said, the holy grail. If we can find a way of making interconnects between hundreds of thousands of little neurons, I mean, of course, synthetic neurons, we're on the way to neural computing. I personally believe, and it's just a bee in my bonnet, I can't prove it, I don't think binary machines can do important jobs like instantaneous voice translation. You call up a guy in China and he's talking Chinese, you're talking English, and it's being translated immediately. It can be done by digital computers, but it's a lot of computing. And I think some type of analog neural computing is going to do that in the future. I can't prove it. It's just, it's not a dream. But it's not a pipe either. But anyway, I think it's possible. And as I said at the start, the only reason for gabbling on like this is to show that analog computing has deep roots, it still exists, it's gone underground into tiny devices, which we now sell for pennies, or a few pennies, literally a few pennies now. So the penny thing is not a joke, we're at that point. In fact, to be honest, or rather to give away the trade secrets, we sell them for 10 cents, so you can guess what we've got to make them for. To get a 90% gross margin. You can do the calculations, but we're there. I think that's enough for now. That's my 45 minutes. That's an hour and a half, by the way, compressed into 45 minutes. So I'm done. And I suppose you guys will have a bit of time for questions if you have any. Or criticisms, even. Am I talking hogwash? Tell me. Yes.
Barrie,
Yes.
What do you think about neural computers?
Yes, well, as I say, the big problem is how do we connect the elements together? And we may have to grow them. I mean, nowadays you can grow fibers. Actually, you can grow neurons too. I mean, you know, the interconnect part. But the neuron I'm talking about is the actual the synapse and the thing does it. It's really integrated. It's actually like a bipolar transistor because there's a relationship called, oh, what's the name of that guy? The law, the rule. I forget. Somebody intentionally came up with a law relating to the fusion of ions across a membrane. And it's exactly the same as the logarithmic relationship of this UJT. In fact, there's a numerical part up front which looks empirical, but if you sort of dig into it, you find out it's KT on Q. So a neuron has this bipolar transistor-like characteristic, but it's also an integrator. So it's a GM upon C thing. And then, of course, there are many inputs. Some of them are, additive, and others are suppressive. There's other words for them. And then eventually it has to trigger and say, that's enough. This information is worth passing on to the next neuron. But I mean, the individual cells can be very simple and beautifully made in CMOS. It's, it's just made for the job. But how do you connect them all together? That's the big problem. Because, our human neurons, I mean, mammalian neurons, have thousands of inputs. Literally thousands. It's amazing how dense, this material is. We could talk about the brain until, the end of the day. It's rather an amazing machine. But I think neural networks have a future, but they're damned right now by the incapability of connecting all the bits together. Carver Mead, when I was with him the last time, said he found a solution to that. He said it's not a three-dimensional problem, it's a two-dimensional problem. I never did find out what he meant by that. He's a bit inscrutable anyway. Anybody else? Yes, sir.
What do you think of the chemical processing in the future? Because right now the digital circuitry with advanced technologies are using like less than 1 volt per supply. So the power consumption for the digital processing probably is promising. So how do you compare it to the future?
Yeah, well, it's a grievous question because I have to admit that there's so much power available in a tiny processor that it's very seductive, very addictive. You really want to get into that domain as quick as you can. I'm not sure about this future. I mean, having grown up through this path from young years to today, I'm bound to stick up for analog methods. But I couldn't really defend them. I think that in the long run we're going to see an erosion, but it's already happening, of course, an erosion of the analog content with the help of digital corrections and so on and so on. But our focus has been to make the analog part as accurate as anybody can by the use of precision resistor techniques. I mean, thin film resistors are very precise, laser trimming to add precision, certain layout techniques to improve accuracy and so on. So, we've been focused on that, and we're bound to be a little bit, what you say, analog-centric because of it. Bound to think about how to, I mean, this analog array normalizer, for example, is a very simple way of taking not just 16 channels. I didn't mention that there are 3 terminals that could be connected together, and you could parallel up as many of these devices as you want. So you can say take 256 inputs from sensors and immediately come out with the normalized value. So one of them is full scale and all the rest follow ratiometrically. I don't know how quickly you can do that, or how much power or how many joules of energy it would take to do that in a processor. The way processors are going, it probably is very competitive. I think the analog normalizer would take more power than a clever processor would. So we're at that juncture, and in a sense, it's sort of a decision time for people like myself who don't expect to stop working for a long time. You know, to what extent should we embed digital parts into our analog circuits? And we're beginning to do that already in a very modest way, but we're beginning to go down that path. But you're quite right. And of course, but the other thing to mention, I think you're talking about maybe a 65 nanometer kind of a node, and that's very expensive if you want to run products on a whole wafer. You're lucky to get a little bit of the wafer, you know, square centimeter, whatever. But you know, the mask costs are getting on for $1 million just to make the masks, and the wafers themselves are very expensive. So you have to be dead sure that this product is going to sell by the millions, because you can make millions on a 300 millimeter wafer. So it's a dilemma. But you're quite right. I think in the end, digital's going to win out, but we'll see. Thanks. Okay, well, I didn't hear any laughter, but I hope it was entertaining. Yes, sir.
One of the obvious advantages of digital computation is we can easily reconfigure our processor to do whatever we want.
Yes.
But if we're selling these, you know, this block that does a logarithmic multiplication,
Yes.
what in the world can we, you know, what can we do to make it more configurable?
I think the thing to bear in mind, I understand what you're saying. The thing to bear in mind is that there is a big demand for these functions. People want to measure the RMS of RF signals, the microwave and beyond, 60 to 100 gigahertz range. And we have a part right now that's in silicon. I mean, it's out of silicon, it's out of wafer fab, ready to be evaluated. It actually is a power detector whose intrinsic bandwidth goes to beyond 100 gigahertz. And it's about 2 milliamps from a 3 volt supply. And if that works out, that is going to be a very valuable general purpose part. And I think the emphasis is still on general purpose products that have a long, long lifetime, because one of the characteristics of modern ASICs is they don't live very long. And they cost a lot of money to make. For us, it's about $1 million per product. So if you're going to spend that much money and invest that much effort into a product, you want it to last for at least 10 years. And I'm gratified to say that many of the products I designed 30 or more years ago are still selling, making good revenues, not to pay the electricity bill. You know, so I'll take the lumps of it. I have this 3-letter acronym, TTO. You've heard of TTM, I'm sure. You haven't heard of TTM? Oh, you're going to come up against TTM. Oh, you've got a lot to learn. Time to market. It's not a research project now, it's real life. And you're given a mandate to make something, and you've got to do it in a week or a few months usually. But no, time to market has a huge pressure, because the idea is that, well, we've got to get there before the competitors do, and so on and so on. I have this really acronym, TTO.
It's a time to obsolescence.
Yeah, it's very good. Time to obsolescence. To me, that's more important. If you're putting a lot of effort into something, you want it to last for a long, long time. And there are these fundamental functions that people time and time again want. Even discrete transistors are still being used, discrete resistors. There's still a big industry to make these things. So some things last for a long time, even though they're overtaken, at least conceptually, and you know, most people, I mean, nowadays, if you ask any person in the street, is digital good for you? Has it made a difference? Man, she sure had. I mean, my iPhone, my digital TV and all that, they're told that digital is better. And in a certain way it is. But it's a pity to neglect the fact that behind all these digital monsters, there's an analog mother that makes it all work. Even a power supply, I mean, it's an analog concept. So I don't think analog is dead, but I do believe that its domain of applicability is being eroded by digital techniques, and rightly so. I've got nothing against that. I just want to get a few more years of analog circuits out of my head before it's too late. Yeah, I mean, those comments are, you know, they're the sort of thing I would expect you to say, because you've been told by some people, some people, that everything's got to be digital. Well, just if you're interested, no.
I'm just
I just waved my hand.
But you were pointing at him.
Okay. Certain people. And there is another approach to electronics, and that is to exploit these rather wonderful, basic, fundamental principles that analog circuits in general have. L's and R's and C's, and energy. Well, of course, energy is a consideration in digital as well. But you can do a lot with these very simple fundamental ideas. It's true that you can still devise new topologies out of just 4 or 5 transistors. I'm doing that, so I know it can be done. It amazes me that, gosh, I thought of every connection, every possibility of connecting 4 devices together. And they turn out to be useful topologies. That's the excitement. The excitement isn't in putting lots of logic together and making it do complicated numbers. I find that less appealing. It's kind of like working in a typing pool. You're told this is what must be done, and you guys go and do it. And we're on the other side. We're saying this is what you must type. So anyway, I'm talking too much. I thank you again for coming. It's a nice crowd, made it all worthwhile. I wish I'd given a more theoretical, technical talk, but I've got plenty of them to give. Maybe next time. Okay.